All right, we need to compute each limit, but we're probably going to be working with L'Hopital's rule because we'll have some indeterminate limits. If I go ahead and just substitute in here, I would get 1 minus 1 minus 0 over 0, which means indeterminate. So if I take the derivative of both the top and the bottom, okay, I will get, let's see, t e to the t minus 1 over 2t. That's also going to be indeterminate if that's 0 minus 1 over 0. So I have to do it one more time. All right, this is a product rule, isn't it? So it's e to the t plus t e to the t with another t all over 2. Now I can substitute in 0. This becomes 1 plus 0 over 2, or 1/2. All right? B. All right. We don't want to work in cosecant. We're actually going to rewrite that cosecant as 1 over sine. So this is the limit that we want to do as x goes to 0. So I think what I want to do is take the derivative, because this will be indeterminate. The derivative of x is 1. The derivative of sine is cosine, right? And if I substitute in 0 for cosine, I get 1, so my limit should be 1. All right. So we got next. Find the global max and min for this particular function. All right? All right. Now, I tend to want to write this as x over e to the x squared over 2. So I can get rid of that negative exponent. So if I take the derivative of this, then I use the quotient rule, right? Which is f prime g minus fg prime over g squared. So derivative of the top is 1 times the bottom minus the top times the derivative of the bottom, so e x squared over 2. Notice that the derivative of x squared over 2, bring down that 2, it's just x, isn't it? So I'll have another x right there, over e to the x squared over 2 squared. So I'm going to factor out e to the x squared over 2, and I will have left 1 minus x squared. And then on the bottom, e to the x squared over 2, e to the x squared over 2. I'm just writing that so that I can cancel that out. So my first derivative looks like 1 minus x squared over e to the x squared over 2. Well, if I'm going to set this equal to 0, notice that this e to the x squared over 2 is always positive. It's exponential growth. It's always positive. So I just have to look at my numerator. Set that equal to 0, and I will find out that x is plus or minus 1. Okay? So if I want to figure out whether these are max or mins, right, on this interval, so we're going to go from -2 to 2, and I also have -1 and 1. These are where my derivative is 0. So I have to check the endpoints of the interval. That's important. So I'm going to check endpoints of interval. So I'm going to do the original function. And I said if I plug in -2 into the original function, I get something on the order of this. If I do -1, I get this. If I do, I get 0.6065, and this is 0.27067. All right, so what that looks like is, if I say here's from -2 to 2, I'm at, no, I just put a 0. So I'm in here, I go down a little bit, whoops, go down a little bit at -1, and I go up a little bit at 1, and come back like this. So that means this is my global min, right? And this is my global max. X equals -1, X equals 1. All right, so we have gotten through sample 3. We're going to move into sample 4. I really like this first one. It's kind of fun. It says find a cubic polynomial, and you start with something that looks like this. We have to find all the coefficients, right? Well, they're telling us we have a local max at x equals 1. That's a local max. We have a local min at x equals 3. So that tells us the first derivative at these numbers has to be 0. We have a y-intercept of 5. Well, that's usually the d. So the constant is the y-intercept. So we know that d equals 5. And then they say an x term whose coefficient is 1. So that means a equals 1. So this becomes y equals x to the third plus bx squared plus cx plus 5. Let's take that first derivative. 3x squared plus 2bx plus c equals 0. Well, they've told me if I was going to set this equal to 0 and factor and solve, I would get x equals 1 and x equals 3. Well, if x equals 1, if I had found the factor that gave me that, this would have been the factor, right? If I had x equals 3, x minus 3 would have been the factor. So I know my factors look like this, okay? And if I put those together, I get x squared minus 1x minus 3x plus 3. Well, I don't quite match because I need a 3 in front of the x squared. So I actually can multiply this whole thing through by 3 to make that happen. So now this looks like 3x squared minus 12x plus 9. That's my first derivative. So guess what? This means that the coefficient in front of the x, negative 12, equals 2b, right? And that c equals 9. C equals 9. So this would be b equals negative 6, c equals 9, and we already knew these others. So it comes out to be x cubed minus 2x squared plus 9x plus 5. Right? So this is good to remember. If they give us the solutions, we can get the factors. We multiply them together and we try to get them to look the same as this. And getting the 3 in front of the x squared helped. Okay. It says a landscape architect plans on enclosing a 3,000 square foot rectangular. I'm going to call this x, I'm going to call this y. She's going to use shrubs that cost $45 along 3 sides, and fencing that costs $20 along the 4th side. So let's say we're going to use the cost function is $45 times the two of the x sides plus y, and then $20 for the remaining y side. And that's what we want to minimize. But notice, we want to get x and y in terms of one of the variables. So notice that y equals 3,000 over x. So I can plug that in for y. So 45, 2x plus 3,000 over x plus 20 times 3,000 over x. So that's 90x plus 45 times 3,000 is 135,000. And I'm going to rewrite this as x to the minus 1 plus 20 times 60,000 x to the minus 1. All right, collect like terms. I'm going to put these two together, right? X to the minus 1. Here is my cost function. So I want to minimize the cost function by taking the first derivative. 90 minus 195,000 x to the minus 2, right? Set that equal to 0. I think the video is going to end here, so I'm going to stop here and pick it up on the next video. So we're into